A very good afternoon, everyone. Anyone, any doubt in the multicollinearity that we did yesterday? I'm just assuming that you are practicing all those steps in your Stata with the classrooms. It's just my assumption. I don't know actually what you are doing, but I'm taking this assumption because if you're attending tabular classes, then it's better you can practice these. Otherwise, as you move to the another steps after this part 3, you're going to start missing many things because this part 3, this part 1 and part 2 is the base for part 3, and this part 3 is the base for part 4. So I think you are doing that. Okay, so come to the next topic. Today we have to discuss about the another OLS assumption that we took, that is homoscedasticity. So today we will discuss this assumption, violation of this assumption, and how harmful is this assumption for hypothesis testing. What are the consequences before that? What this particular problem is, causes, consequences, then few detection methods, and most probably tomorrow I'll take few remedial measures for this particular problem. Okay, so let's start with this particular problem, heteroscedasticity. Suppose just try to understand what this particular problem is. This is that variance will change as you move from one level to another level. First, just try to understand with cross-sectional, and mainly this problem we will find in cross-sectional data. Uh, Hardly in the time series data. This is something with the cross-sectional units. Okay, just try to see these two graphs. This was the assumption that we took initially in the OLS assumptions. Now, this assumption means equal variance of this residual term. Now, if any one of you done all the derivations, can anyone from you tell me that where did we use this particular assumption in the derivation part? We use this assumption in the derivations. Any hint where we have used this particular assumption? In that particular area, it will create problem if this assumption will not fulfill. Okay, you can for the time just you can think about that part of the derivation that where we have used this, and for the time being, let me explain this particular problem. This is that variance is not same in all the levels of your particular independent variable. For example, let's take a saving and income example. So as initially I explained this in the assumption part, that we have this thing in mind that at all the levels this variance will be same. Let me explain this with the diagram. Now I'm giving you a hint as well. In these derivations, we use these assumptions, and I'll come to this particular point in the consequence part, that what are the consequences to this particular problem. But before that, try to understand this nature of this particular problem. Why this is not working. Okay. I'm taking the same example that we took in the type of during the assumptions. This is your wages, this particular variable. I don't know why this is creating problem today. Okay, let's pose the initial model. Okay, just first take this example from the book, saving and income. Now, as you know that regression equation generally pass to these both the means. Let's say it is a y variable, it's a x variable. Let's suppose this is our regression equation. Y hat equal to beta 1 hat plus beta 2 hat x variable. Now, all these regression is near the regression line. There are the actual values, right? So the assumption was this homoscedasticity assumption was that this particular variation at all these levels, let's suppose these are the different levels of income. Let's just take this first case with this particular level of income. The variance is this is particular variance. Now, what this variance is all about? These are the actual values, and this is y hat regression line. Actual value minus y hat. What this represent? U hat, right? So this is the variance of U hat, the variation around the regression line. The assumption was that this particular variation will remain constant throughout the different levels of your independent variable. This variance will remain same at all the levels of your regression line. First, okay, this assumption is clear. This was the assumption, and this was the homoscedasticity, where we are saying that this is what was the assumption, that this expected square U hat square is equal to constant variation. This is constant variation at sigma square. Actually, in this bookish example, this part is for population, so they are using ui square. But if it's a sample, then I would say this is expectation of u hat square, and that's something constant. Let me put it in both the ways, for population first and then for sample. This u hat square is equal to sigma hat square, means it's constant. And we have proved that, so this is sigma square, and this term is from the population, right? But we have used this particular term in place of this in all the derivations. And for that, we have proved that expectation of the sigma hat square is equal to sigma square. And that's why wherever we have this expectation ui square or expectation u hat square, we have used this particular term. Now, first try to understand where are the places where we have used this particular assumption. First, to prove this derivation that on an average, the variances of these samples residuals is equivalent to the some constant variance. And for that, we have used this assumption. If you remember this derivation, here we have used this particular derivation. Here we have proved in the end that expected value of this sample variances is equivalent to the population variance. This we have proved, and here for this particular proof, here we have used in all the places wherever we have expected ui at square, there we have used sigma square because of the assumption of homoscedasticity. And besides this particular derivation in the variance of beta 2, if you remember the derivation of variance of beta 2, again we have used this particular assumption. Here where we derived this variance of beta 2, again we use this particular derivation, right? And here we have assumed that this is constant variance. That's why our variance of beta 2 is this particular formula. So in these two, means in these all the derivations, we have used this homoscedasticity assumption. So now it's crucial that what if it's not homoscedastic? Now what it means that this variance is not constant, it's changing. Means we assume that this is constant, right? Like it will not change. What if it will change? So first tell me that, is it clear that what it means? What it means that it is homoscedastic, and there are the places in the derivation where we use this particular assumption. Then only you can understand the problems with violation of this assumption, because then you can understand that in all those places, if homoscedasticity assumption is not fulfilled, then results are going to be changed. What, Gagan, which part you want to repeat? Pallavi, is it clear? It's homoscedasticity. Okay, diagram. Okay. Okay, Gagan. That's why I'm saying to all that this econometric course is step by step. Means if your homework is not properly cleared, in the next all the coming steps you might face problem. It's not like this econometrics are totally different. Means it's not like the development economics or macroeconomics. Although in macroeconomics also it's level wise. Like you start from this Keynesian aggregate demand theory and then aggregate supply, and then in the end you reach to the ISLM curve. That's in ISLM you need to know about all the previous things. Similarly, this is in econometrics. If your first part is not clear, then in second part you will find it difficult to correlate the things. Means that's why I tried to explain this thing, that in masters and in many places in state universities, I have seen in private universities as well, students are just cramming these derivations and concepts. In practical understanding, they don't know anything about it. What it means, what these assumptions actually, what it means, and how they are going to affect your results. but they actually do in the master courses because they are not going to run any of the practical regressions. So they just cram these things. Means they, some of them really write wonderfully in their exams, all these derivations and everything. But practically, if you ask them what it means, they don't know actually what this means. They just crammed and they're just writing the exams. That's the problem with our system. And the next problem with is that later on when they become a teacher, they teach by a same method, and means they don't even know what exactly that means, and they are teaching. And I have seen in my experience in last 3 or 4 years, the teachers who are teaching econometrics means it's not at every place. I mean, like, I'm not saying that everywhere, but in most of the colleges and the state university and private universities, they are just trying to give the derivations and all to the students, and just they expecting the students can cram all those derivation and write in the exams. Practical application is not so far have they have introduced in their syllabuses, and it's not true for this JNU, IIT, and all those good institutes. That's the difference between these institutes that I told you this in the first story, that we have this three-tier system. Uh, Topmost institutes, intellectual developments, and then in between and in the lower layer where the majority of students are going to train. There, this all the practical applications are not available. The real thing to need to worry is that they don't even know that what exactly is practical application and why it is required. They are so much overconfident that they are teaching in such a manner that they are thinking that they are teaching econometrics wonderfully. No, no improvement is required. Means I am surprised by their level of confidence by just teaching the derivations and theoretical part. That how confident those teachers are, and it means that their dimension is limited to this particular knowledge. As I am saying that whatever students are studying today, tomorrow they are going to teach same thing in the college or state universities. So that's the whole system, is that's how they have this class this particular thing. Because what I found that to understand these econometric applications, it took a time for me as well. Means every time I found some one or the new things in these chapters, so it take a time. Okay, so as Gagan is might not getting this point, that what this homoscedasticity is meaning. Okay, take another example, this wage and education, the regression we are doing. Wage is our dependent variable and education is our independent variable. It's X variable, it's Y variable. And you always have to keep this thing in mind that when we are doing the derivations are also trying to prove at many places uh, with the population as well. It's not all the derivations are with it. Like this unbiased property, the Y value we are taking, that's for the population, that summation Ki yi, that yi intentionally we took because there we have this unbiased, residual and uh, parameters for the population, and we prove that expected value of our beta hat is equal to 2 population parameter. Similarly, we have proved that expected value of sigma hat square is equal to sigma square. So wherever we have to use this particular variance, we are using this particular. You can see this all the derivations in the variances. We have written sigma square, not sigma hat square. At all those derivations, I told you that we are using it because of the homoscedasticity as an assumption, and we have proved that this is equivalent to this. And this particular part is from summation u hat square If it's bivariate regression, it's n minus 2. And from the here you have to get this particular value, but in the derivation part, at everywhere in place of this we have what we have used this particular thing. Similarly, wherever we have expected ui square population part, again we have used and we have said that this is assumption of homoscedasticity. So just try to concentrate what it means. Expected value of ui square is sigma square. So what expected means average of ui square. That is, and now what is your ui square? That is actual value minus y hat. Now what are your actual values and y hat? Let's suppose this is our regression line and all these are actual values. Regression line is always y hat, right? Beta 1 hat plus beta 2 hat x if we have only one independent variable. Now what this means? It means that the ui square, its expectation, this particular variance. If it's a sample, then it's a u hat square by n minus 2. It means that variance at all these levels, all these different levels of x, this particular variance. This is constant. Constant means this particular variation around the regression is line same throughout the regression line. This is homoscedasticity. Now first, I'm trying to clear that, try to understand what homoscedasticity is meaning. Means theoretically this is the meaning, and then you have to identify in all the derivations where we have used this particular assumption to derive the formulas. But before that, just try to understand what it means, because when actually you are going to run the regression, then you need to know this theoretically, that what problem it will create if this particular assumption will violate. So this is but this variance is this particular changes are what? This is actual y minus y hat, right? So that is our residual term, u hat. So what this variance is about u hat, right? The gap between these actual values and this regression line, this particular variance around the regression line, that is the variance of this residual term. So we are saying at all the levels, this particular variance is constant. That's homoscedasticity. I explained you this in the beginning in the assumptions class. Means I don't know why you not have asked this question in that particular class, that what it means. But maybe you are not revising these things. I already explained this in the assumption part. Okay, so first this is the assumption that this is constant. So always we have used this sigma square for this thing, right? And if it's sample, it's a sigma hat square. But we have proved that expectation of sigma hat square equivalent to sigma square. So in all the places we have used sigma square. Now this is the first part, that what this assumption is all about. Now second, try to understand where we have used this particular assumption. First, we have used this particular assumption to derive the variance of beta 2. If you remember, the variance of beta 2 is, there we have used this particular equation, expected summation ki ui. If you remember all those derivations, if you know, then you just go back. And there in this particular case, we have used expectation ui square, and in its place we have written sigma square, because we said this is a homoscedasticity assumption, and this was the derivation of variance of beta 2. I'll come to this particular point again, that what if this is not constant, how these results will change. But now at least you can get this hint that variance of our estimates is going to change. Means if you like yesterday, the one of the main problem with the multicollinearity is that standard errors are increasing because of increase in the variances. So today again variances are going to change. Now I'll come to later on whether it's going to increase or decrease, but variances are going to affect. And how variances are, why variances are important? Because our hypothesis testing, either you can use this uh, t-statistic approach for the individual significance of the coefficients or confidence interval approach. This depends upon the standard error, and if standard error will change, this results based upon the hypothesis testing are going to change. So now you can get this hint that today also now going this standard error is going to change, and that will affect our hypothesis testing, confidence interval as well as t-statistics. So before that, now just come back. So if it's not constant, then what will be the case? Now see this particular second case. This is not constant. That the saving and income behavior, the variation in income uh, throughout the regression line is not constant. At small scale of income, variance is less, but at the large scale of income, the diversion is much higher as compared to the lower level of income. So variance is not constant. Variance of residual term is not constant. Now, how it will create problem, I'll get that particular point, but first try to understand it's not constant. If it's not constant, that means we say it's a heteroscedasticity, and that's the problem. So now I hope you got that this is what it means if it's not constant, what it means when we say it is constant. So if it's not constant, if you go by this Gujarati, they write it as a sigma I square, means it will change with all these levels. It's not constant. So now I hope you got this point that what heteroscedasticity. Now come back to this example, wage and education. Then what will be the alternative situation if it's what if it's not constant? Although it's not my intention to criticize the teachers or any system or something else. It's not their fault. Means like what I have read and studied in my masters and my courses, that's what I can teach, right? So if there is some fault in my teaching, so that might be that I'm not putting effort. So it's not that we can blame anyone for that. But I'm just trying to point it out that this point is true, means, and I'm only worried that the students who are teaching these courses in their masters, they only have a one chance, right? In their whole lifetime, they have this only one chance when they teach this, study these subjects. And if by any chance they are not studying these subjects in the true manner which is required, then there is a loss for them. And we don't know how much loss is for them. It might impact their PhD courses, their MPhil courses, their research tasks. And generally, after economics, if you do masters in economics, your job dimension is it's a research type, right? And if you are in a research domain and your background is from economics, everyone expects from you this regression analysis. Means the levels might differ, but you can go any places. They definitely will be connected with these type of jobs. And there, if you are not able to do that particular task, or even don't know that what problem you are creating, so that's why I'm saying that this thing is it's not good. Means I hope teachers can try to understand that whatever subject they are teaching, it's not only about the econometrics. Try to teach them with a practical manner and try to look upon some good universities that how they are teaching. Like just go and visit any of the good university and just try to collect their notes and the things from their students that what they are teaching, and try to learn those things and then try to teach. That might take a 2, 3, 4 years. This is not a, but that investment we have to put. If we are in the teaching profession, that investment we have to do. Otherwise, we are not justifying our job. We are just doing a copy paste. Then what's the difference between teacher and a photostat machine? I don't get this point. If I have something, I'm just teaching same thing. So that's just a photostat machine, right? So that we already have. Why we need another photostat machine? Okay, so the alternative situation, that it is not constant. Now try to understand in the cross-sectional data. In the lower level of education, let's suppose take a case of India. Okay, just take urban area. Let's take till 8th class standard. Now you can just imagine that those who are just 8th passed, what type of jobs they can do. They might be a rickshaw pullers in a transportation type, in a casual labor, in hotels, dhabas, constructions, factories, all these workers, right? Those who have a low level of education, they have a variation in their income, right? Means definitely they don't have the same income, but the variation might be a less because more or less these type of jobs are going to provide you some basic level of income. Now come to a higher level of education. Just take a case, graduate and above. Okay, this is how in India we have education. Now you know that the variation in graduate and above, they might be in a call center earning just a basic income, or they might be doing their own businesses, have a variation in income. They might be in a corporate sector earning some high levels of incomes. But the thing is, with the income, what do you think? The variance will increase, means this variation will increase in this large education group, those who have a better education compared to, because here the variation in high or low professions is higher. Means that's a theoretical notion now. It's not that I'm correct here. It might be vice versa, that this variation is high here in this lower case and low in the higher case. Or it might be the third case that this variation will be constant. But if this is the case, this is the one of those possible cases, then it's not that we have a constant variation, right? Now here the variation is much higher. This is hypothetical, we create this situation, but it's possible in a cross-sectional data, right? And as I told you in the beginning, this residual term, this actually variation is about residual term, and residual term is actual y minus estimated line. And this is due to all unknown factors, right? Now here the unknown factors are so much. Means wage is not only depend upon education, it depend upon, means just unknown factors. It might be a function of parental education, parental occupation, uh, area where you are living, means might be like few areas are good in business opportunities, others are not. It might be your financial position, your skills. It's not only that your education level, but which type of course you have taken. So there are n number of factors. So if these unknown factors will create a variation around the regression line, yeah, it might be experienced. If it's a constant, means all these unknown factors, the changes they cause in this around the regression line. Thing is that, is it that these changes are constant, means some variation, specific variation level, or this is not constant, it might be high or low. And that's the more genuine case in the cross-sectional data. So if that's the case, then we can't say this is the constant variation. Then we have to say that this expected value of u hat square is not some constant number. It's change with the I. Means with the change in the level, this particular variance will change. So that's the heteroscedasticity. So now I hope it's clear what heteroscedasticity is. Now I'll come to a first probable causes that but which things can cause this type of changes. But before that, now I hope it's clear that what is heteroscedasticity. It's theoretically for you, it's clear. And now, whenever you run this regression, just think about it. Like, let's suppose we have this data for wages and education. So let's see the case here that how our regression. Okay, before that, you have to first regress, then you have to predict y hat and then residue. I already saved u hat, so I'm directly going to jump this particular variation. Two-way scatter. Now I want to, sorry, u hat square with wage dependent variable. Okay, so this might be a case here. Now you can see that wage and u hat square. This situation is changing, right? That our dependent variable with the u hat square. So initially this variance is somewhere this, but this is the variation, and now this range is changing. So this is something, or you can see this with the predicted value. In place of u hat square, just try to look at with the pi hat. Is it constant or it is changing? Now you can see here clearly that this variance is not constant, right? This is changing. Here the variance is small, like I'm saying in the lower level of education, and then it is increasing. So it's not constant in this particular case. So that might be a situation you have in your, if you're doing a primary studies, and that's mostly on the cross-sectional data, right? Primary studies are on the cross-sectional data. So here you have to take care about these things, that heteroscedasticity. So, okay. So heteroscedasticity meaning is clear. Now, before consequences, let's try to understand what are the probable causes for this heteroscedasticity. So today I'm going to use one of my assignments during the coursework which I had done already during MPhil. So I'm taking this particular, and I used only 2 or 3 reference books during this assignment. Gujarati and G.S. Madala, Woolridge. I think Courtesans only have a small chapter, not even a chapter, just a few pages on heteroscedasticity. So I refer you, either you can go by Madala, Woolridge, or Gujarati. But better to understand, go by Gujarati and then try to read few extra things from Madala and Woolridge. So what are the probable cause of this heteroscedasticity? Now, when we will say heteroscedasticity, just try to understand that it means this variance is not constant. It might be any situation. Initially, it will high, then it will decrease, or initially it will low, and then at the higher education level, it will increase. Uh, it is with all Pallavi and Prerna, or do I am audible? Okay, Gagan, just check your internet. Because to check this voice, what I generally use, I connect both phone and laptop. From the one side, I'm just also listening that what I am saying, that is it audible or not. So whenever it will be, I'll get this call. Okay. So first thing is, now again, this is the probable causes. It's not that always this is the situation. As yesterday I told you that that's only the examples I took from the Gujarati. It might be any other reason. Error learning models. Now, what error learning models is that? That again, all these examples are from Gujarati. Initially, okay, just take a example from. Is it any other example? Okay, typewriting error example. If any one of you have done any this, early we have a typewriters, right? Might get surprised. I also did that means for 5 and 6 months. That typing with the old typewriters, that tick machine. Oh, that's very tech. Sometimes, if you any one of you have tried, it's not easy to adjust the page correctly in that particular machine. Okay, just take example of laptop. If you're doing a typing, initially you do many mistakes, but once you get experienced in that particular exercise, your mistakes will get reduced, right? So here just think in type of mistakes, this residual term. So it might be some error learning models, like initially your models are not, means it's not correctly formed, so you might have a problem, but then by the time your variances will get reduced. As people learn or practice more, their errors decrease over time, thus variance is expected to decrease. Then if your variable is related to income, then discretionary, let's suppose you have any of the variable which is related to discretionary income. So this is a phenomena with the income that in all the levels, all the income levels, this saving behavior, the extra income you have. Now, how you can manage that extra income, that depends upon you. But that discretionary income, the managing how you manage your discretionary income, this thing is not same for the lower income group and the higher income group. Means if you are at a higher income group, you have a many possibilities where you can use your extra income, like you have investment options, you have a saving options, you have a post office saving incomes, life insurance, mutual funds, stock market, or bond market, government securities, share market. But if you are at a lower income group, then you don't have all these options, right? Either you are going with some basic insurance scheme, or you are putting your money in as in a fixed deposit in a bank. So at lower level of income, the variation is within the behavior of discretionary income is less as compared to the higher income level. So that's one specific case, means if your variable is with the income. Then skewness, if your variables are like income, wealth, education, like this example we have took right now, these data are not normally distributed. I mean, these variables are not normally distributed, right? This education and all this income and wealth. At higher levels, they have more variation. At lower level, they have only few basic things. So again, it's not going to be a constant variation. Then variables are measured without errors. Another assumption underlying the linear regression model, that measurement of errors, some respondents might provide more accurate response than others. It might be like that you are doing primary survey and you have two different groups, that one is higher educated, that might give you information more accurately as compared to another group just not able to understand your questions. So that might be a problematic. Then data collection techniques. So data collection techniques, now in the cross-sectional data, the thing is, in all these cases, don't just think that these cases are only about one particular sample, because when we study like for PhD or research paper or these things, we do a primary surveys, or we're taking secondary data. We have a specific means data for a specific time, right? But and for a one particular sample. But these examples in textbook, that might be for the combination of all the different type of samples. So then like this data collection technique. maybe initially you are not perfect or you are not experienced how to collect the data. By the time you try to reduce your mistakes and you learn many things about data collection techniques, that might reduce the variance, right? Then specification bias. This thing I'll take in a specification model specification test in part 4 in the beginning, that if your model is not correctly specified, that also create a problem. Then outliers, like in this education example, if you see the original graph, wage and education, there might be outliers in data. Yeah, this particular, okay, this high level of education, you can see there are few outliers, like if they're exceptionally getting higher wages. It might be like income, like if you go by profits of the this self-employed, then there are few entrepreneurs who are getting much higher wages. But there are sometimes outliers, and these outliers change the variation around the regression line, and this might create a problem of heteroscedasticity. So when you have a primary data, then always try to look upon this angle as well, that is there any outliers in your data? Then you have to deal with them accordingly. Then like other technical faults might be like incorrect data transformation, incorrect functional form, means your overall model. This now you can just see this, out of this 9, 4 or 5 probable causes of heteroscedasticity are related to your model specification, how correctly you specified your model, and 1 or 2 with your data collection. So it might be that because of your some sampling design, mistake in sampling design, in your data collection technique, or in your model specification, or in proper uh, equational form, you might create this particular problem of heteroscedasticity. So means few of these are related to your model specific thing and how you collected your data and sampling design. And few of the things are the nature of these cross-sectional units, like these variables: education, income, wealth, savings, behavior, and there are many other social factors as well, where the variation among the individuals is not same at different levels. It might change. So it might be the nature of the individuals, means that particular variable in hand, or it might be that because of some type of error in your model and data collection method. So that might change the variance around the regression line, and that's the heteroscedasticity. And it might be any other cause. Means the thing is that if this variance is not constant, any other reason beside this reason, that's also be a probable cause for this heteroscedasticity. Now, if heteroscedasticity is there, the next thing is, what are the consequences? Is it problematic? So now look upon it. Okay, yeah. In all the assumptions, all the derivations, at many places we have used this sigma square, wherever actually we have to use expected sigma hat square, because we have this assumption of homoscedasticity. Is it clear? At many places we have used it. Now just see the examples that where we have used it. In the derivation of variance of your estimates, like this, variance of slope coefficient. Here we have used this assumption, and at place of expected u a square, we have used sigma square. Means we have this assumption of homoscedasticity. And because of that, in end, our variance for beta 2 was sigma square by summation xi square. Now think, what if it's not the case that this is not constant value, this expected ui square is not a particular constant value, then what will be the variance? Is how it will change the outcome. So just see this example from the textbook itself, that our variance is going to be changed now. So earlier we have this particular variance, but now our variance is going to be changed because it's not constant. And if it's not constant, so if you remember this derivation, if it's not constant, then this thing is going to be with sigma I square. So in that case, this particular variance is going to be summation xi square sigma square by summation xi square. Is it the case? Yeah. This numerator term, you can see this is changing because it's not constant. This is because of heteroscedasticity problem. Now, why this is the case? Because if it's not constant, then it's not that this thing is going to be out of the summation. Now it is going to be within the summation. And if it's within the summation, then it's this xi upon summation xi is not, this xi square is not going to be a cancel out. So now the final solution is summation xi square sigma I square by summation xi square. Similarly, other slope, partial slope coefficients are going to impact, but it's not the early case where we have this particular variance. So now just think, is it that variance is increased now? In this particular case, now numerator is going to increase. So it means our standard error is going to change. And if standard error is going to change, then hypothesis testing is going to affect. So now let's see what is the consequence. If heteroscedasticity exists, we cannot apply formula of variances to coefficients to conduct test of significance and to construct confidence interval. The tests are inapplicable. The variance of parameter is no longer constant. It rises with observations. When variances are larger, the standard error is large and the calculated t becomes smaller, as we did yesterday, and coefficients become insignificant, though we may have correct variables in the model. So that's the consequence of this particular heteroscedasticity problem. Now this is not the formula we are going to use because it's not constant. So now we have summation xi square sigma hat square divided by summation xi square. So that's the problem with the heteroscedasticity. Is it clear? Is this point is clear to everyone that this is now going to change because this is not constant. This is the one of the consequence of this particular thing. And second, this proof is now not possible. We proved this thing, and then in all the places where we have expected divide square, we use this sigma square. It's not possible. So both the things are not possible. So the probable cause is that our standard error might get increased and variables get insignificant. So that might be a consequence of just because of heteroscedasticity. Is consequences clear to everyone? Gagan, Pallavi, or Siva, Saror, Prerna? That this is going to change and it will increase our standard error, and if it will increase our standard error, hypothesis testing is going to affect, because in hypothesis testing we are using standard error in confidence interval approach, in p-value approach, and in test of significance approach. So this is the consequence of heteroscedasticity. That's why this is problematic. This whole hypothesis testing, these results are going to change. Okay, if it's clear, then I'm going to move towards detection. Means if you are clear with the consequence that this is problematic, then thing is how you can detect it. So let's do few methods of detection of heteroscedasticity. So there are a few graphical and other tests of heteroscedasticity. So first, informal formal method. Generally, we divide in this particular form. In informal, one of the method is graphical method. Now, graphical method is for what? This whole heteroscedasticity problem is about u hat square. Okay, that's variance is changing. So we are going to see the nature graphical position of u hat square. Is it constant or is it changing? So that will tell us whether there is a heteroscedasticity or not. Like in graphical methods, let me see if their graphs are given. Yeah. If this u hat square is constant, this particular position, like we have here earlier, this graph of wage and u hat square and y hat. It's not constant, right? And after a particular level of education, the u hat square is changing. So that's indicating that this variance is not constant. That's the graphical method. In graphical method, what you have to do, you have to see u hat square with either predicted y variable, means dependent variable, or any of the independent variable. But thing is, if you have a more than one independent variable, then which particular independent variable you want to see the relation with the u hat square? Means in that particular case, the thing is first you have to identify which is the particular independent variable that is causing this change in the behavior of u hat square, and that's only that particular independent variable you have to look with the u hat square. But if you don't want to get that particular thing, then just try to look upon u hat square. Like this particular problem is of u hat square, this particular variation change with the regression line, that is it constant with the regression line or is it changing? So it's better that you can just try to see the graph of u hat square with the y hat. And why u hat square? Because in the variance, the formula is summation u hat square upon n minus 2. So that variance comes from u hat square, right? And we are talking about that particular thing, that is it constant or is it changing? So we have to see that u hat square with a predicted y hat. So okay, if you want to do it in Stata, in this particular wage file, we have a wage and education. So first you have to run the regression. After regression, you have to, okay, let me do it for you. Clear wage one file. First, regress your wage and education model. Then after that, you have to predict y hat. I already have, so I'm not running this command. Then y hat will appear here in end of all the variables. I already have, so it's already defined. Then you need u hat. So just try to predict u hat comma residual. It will give you a u hat. After u hat residual, but we need here u hat square. So for that you have to do generate u hat name. You can give any name. I'm just saying u hat square. It is your u hat multiplied by u hat. That will give you u hat square. Okay. I'm not running because I already have u hat square. So you need a graph of y hat and u hat square. So that's two-way scatter. Within a bracket, your u hat square and your y hat. It will give you a graph like we have here, y hat and u hat square. So this is not constant. Like if this is the case, then we can say this is constant. So it's a homoscedastic case. That's what we want. But if this pattern is changing, is any of these patterns, like earlier we have this u hat square with the wedge, so it means this is not constant. So there is an indication of heteroscedasticity, but this is some informal method in its specification, because it might be sometimes subjective, that how much variation you will say is it heteroscedastic case and how much you are ready to tolerate you. So we need some formal methods. So let's go by formal methods. This graphical method is clear. Anyone, any doubt in this graphical method? Why we are trying to look relation of u hat squared with y hat? Yes, I hope now you got this point. Y u hat square and y hat. You can also see with the independent variable, like in this case, since we only have one independent variable, so we can use that is it that this change is because of this education. Two-way scatter u hat square education. Yeah, it is changing, right? So it's also indicating heteroscedasticity. So now let's look upon few formal methods. So one of the methods that is given in these textbooks is this Glaser test. I don't know how to pronounce this, Glaser or Glazes. Just try to understand this test. The idea behind all these tests, first just try to understand this idea behind all these tests is to identify whether I need some rough free space. Okay. Whether u hat or u hat square is related to independent variable in any form. Means if it's changing, that's the case of heteroscedasticity. If it's not changing, it's homoscedasticity. So in all the formal methods, you are going to see that these tests are trying to look this relation with u hat or u hat square, or might be just u hat module, because negative and all the summation is zero. So it might be just absolute values with the x, means independent variable, that is it that this particular thing is changing, means this variance is changing because of the independent variable, change in the independent variable or not. If it's not, then that's better, that's homostatic. But if it's changing, that's a heteroscedasticity. So in all the formal methods, we see that these type of relations they are trying to identify. So the first method is in this particular method, but they have done that. Try to run all these regressions where your dependent variable is u hat. U hat you will get once you will run the regression. Like here we run this Bayesian regression. Sorry, here. Wage with the education. Then you have a y hat and u hat. U hat is actually actual y minus y hat. Now this u hat you have to run as a dependent variable. And independent variable, these different type forms of x. simple x, then under root of x, reciprocal of your independent variable, reciprocal with the under root or under root of this particular equation beta 1 plus beta 2x, or you had under root of beta 1 and beta 2 x squared. But in these last two expressions, because our these parameters are non-linear, these have an under root, and this is the in the OLS this limitation that parameters needs to be linear, so we can't run the regression for the last two cases. But in all the above cases, these four cases, you can run regression. And then how you have to get this, that is it a hetero or not? If this relation is significant, this coefficient is significant in majority of the cases, then we can say there is a case of heteroscedasticity. Now you might get confused that why all these type of means. It's something, just try to understand that this particular method is trying to look all the combination of u hat, and if this u hat is changing because of x independent variable, that's an indication of heteroscedasticity. You only have to need to run all these regression. U hat or you already have. Here you need an absolute u hat, means module. So for module, you have a u hat square, right? So just take a square root of the u hat square. That's your module value. It might be that direct formula for module. Right now, I don't know that thing. But if you need an absolute value, you had that I'm writing it as a module equal to its square root of u hat square. So that will give you absolute values for u hat. I already have, so I'm not running it. It is generate u hat. Name you can give anything. Then square root of u hat square. That you have to run as a regression in the independent as a dependent variable. First with the just like here you have to u hat with the education, then generate new variable as a under root of x, means just take a square root of education, that's a new variable, another regression, then third and fourth, then reciprocal, then you have to run these all four regression and try to see the results. Like here I had done it 4 times. Here my model is this Angel's curve I am trying to look upon, relation of income and food expenditure. My dependent variable is food, log of food expenditure, and independent variable is log of income. This is log model where we have to see elasticity with the 1% change in the independent how much is the change in the dependent variable in a percentage form. So here now first u hat with the independent variable. Now this is the coefficient, and with the p-value it is significant, right? So in first case it's significant, means this relation is significant. It means u hat is changing with the change in x, so that's the indication of heteroscedasticity. Next case, under root of log of income, so it's a square root of log of income. Again this p-value is less than 0.05, so it's again significant. Third case, it's a reciprocal of log of income, again it's significant. And fourth case, it's a under root of reciprocal, again it's significant. So for all the tables, it's clear that relationship between module of u hat and log of income, that's my independent variable here, is significant, which means that our residual is vary with independent variable. There is a heteroscedasticity. So this is a Glazer's test where you have to test these different forms of relation of u hat module absolute value with the different form of independent variable. If it's in the majority of cases, you have to say there is a case of heteroscedasticity. Is it clear, this particular method? Any doubt in this particular method? Means what we are trying to see? We are trying to see that is it that u hat is related with independent variable or not, like what we have done here. Is it that this u hat is related, this change with this, or is this a constant? If it's changing, that's what we are trying to look by these all the formal methods. Is it clear? Then look upon the next method. Okay, what are the drawback of this method? First is that because of the heteroscedasticity, residual term is not going to be zero. Second, in last two cases where these parameters are non-linear or it is not possible to apply, these are the two limitations of this particular method. Then next method is a simple correlation technique. That why not we can just see the correlation between u hat and our independent variable. If it's significant, it means there is a case of heteroscedasticity. So for this particular method, just you have to run a correlation of u hat and your independent variable. Now, if it's more than one independent variable, then first you have to look upon which of the dependent variable you think is changing the variation around the regression line. So then you have to first identify that. Okay, so we have to apply Spearman correlation. So Spearman correlation, the command is Spearman absolute u hat value, because you have to rank it. Spearman correlation is ranking method, right? With the independent variable. And we have to see its hypothesis testing. Is it significant, this correlation? It's not the question here of the degree. The question here is it a significant correlation? If you run this particular command, you will get this significant. Now, null hypothesis is that this u hat and education are independent, means they are not related, and alternative is they are related. Now, this p-value is indicating that since it's less than the level of significance, so we have to reject this null hypothesis. We have to say they are not independent, they are dependent on each other. So it means this u hat, nature of u hat is changing with the change in independent variable. So that's a case of heteroscedasticity. So this is Spearman simple test we can apply for heteroscedasticity. Is it clear? These are the formulas that we already did in the second part. That simply we are applying it. Then next method is, yeah, let's suppose you have more than one independent variable, right? So then you are not sure that which particular variable is creating a problem. Then you can apply this method, Brush-Pecan-Godfrey test. Now, how this first is try to understand the methodology of this method, and then we can run it with the Stata software. Let's suppose you have this particular model, like wage depend upon education, experience, member of union or not, parental education, form of industry, and so on. Okay, if you don't know which of the X is creating this problem. So first just run the regression and obtain some u hat square. Then obtain average error square, that is simple divide summation u hat square with n. That's the average error square. And then generate a new variable, that's pi, that is residual square divided by this average error square. Then regress this pi on the explanatory variables, dependent variables, and just take half of the explained sum of square, and if that half of the explained sum of square is significant, now you have to see the overall significance of the model, this particular model, that is it the case that they are, if they are zero, they need to be a zero, right? Because that's the case of heteroscedasticity. And if they are not zero, then that's the case of heteroscedasticity. Now, again, just try to understand what they are trying to do in this particular method. Now, just try to understand that the one of the problem is if you have a more than one independent variable, you don't know which of the independent variable is creating this problem. So to get rid of that, it's not here that we are trying to run the regression of one of the particular independent variable with the u hat, but besides that, we are going to run a regression of actually u hat square on all the regression on the all the independent variables, but not actually u hat square. This regression is of this pi. Now what this pi is, now just try to understand this pi value. Okay, let's see if it's possible. Yeah, I think this is visible, right? Okay, just try to understand this process first. We have an original model, like this is the other model. First, just run your simple regression. From there, like wage and education we ran, right? Then from there you will get u hat, but this u hat is actual y minus y hat. And y hat, how you get y hat in this data? Just type a predict y hat, you will get y hat, and then predict u hat residual, you will get residual. Now take its square, u hat square, like we did. Now take its average, this first part. Now in graph, what it means, just try to understand in graph as well. If I can extend it. Although this is not possible because there are so many variables, but I'm just taking case of wage and education again. We have a regression line. With the regression, we have this actual values, and that's tell us u hat this actual minus this regression line is the u hat. That is the first case. Then just take their squares, this u hat square. Now take its average. Now you can take its average. Summation, just take a summation of these all the u hat square values, divide by n. So what it will give you? It will give you average of all these u hat square, all these u hat squares, we will get some average of these. That average might be some any particular number, right? That is this average of residual as average error square. Now, generate a new variable in the data, generate a new variable that is pi. They just give a name as a pi. This new variable is this u hat square divided by this average. Now you have an average, right? Just divide this u hat square with average. You will get this pi. Now run this regression of this particular variable pi on all the regression independent variables. And if its explained sum of square is significant, means if this overall, because we are not going to check this individual significance, but if this overall model is significant, then it means that there is a heteroscedasticity. If it's insignificant, there is no heteroscedasticity. But the one trick they have used is that rather than simply using the F ratio, what they have done is that in place of that, they used half of the explained sum of square. Now, why half of the explained sum of square? You can just try to understand that this pi is a division of with the average already. So it's already divided by the average, this particular variable. So it's not that we can take this total explained sum of square, just half of the explained sum of square. If this explained sum of square, this is a chi-square, it gets changed into chi-square distribution. If this is significant, then it means there is a heteroscedasticity. If it's insignificant, there is homoscedasticity. So this is the Bruce-Pagan-Godfrey test. Now just look upon it again. First run simple OLS, obtain error square. Then from error squares, you can get average of the total error squares. Then divide all the u hat square with the average. You can generate this new pi variable. And run this variable on all the independent variables, regress it. Take its half of the explained sum of square. And the null is that all these are insignificant. That's the case of homoscedasticity. And alternate is it's not equal to 0. At least one of is not equal to 0. That's case of heteroscedasticity. So to run it in a stata, you are not required to do all this exercise. Just one simple command, that is estat heteroscedasticity test. And if you run it, it will directly give you this chi-square value. This value is this last part, this particular part. This value is 52, and the null is that all the coefficients of this regression are 0. But here p value is less than level of significance, so we have to reject the null. So it means there is a heteroscedasticity, and that we also seen in the graphical method that there is a heteroscedasticity. So this is the case that this level of significance is less than, sorry, p value is less than level of significance. So this is a, if it's not equal to 0, means we have to reject the null hypothesis. It means there is a heteroscedasticity. So this is a Bruce-Pagan-Godfrey test. Is it clear? Anyone, any doubt in this particular test? Means what directly what they are doing, just if you can try to understand. It's not that simply they are running u hat square with the x. Now you might have a many independent variables, so you are not sure which of these creating a problem. So in place of this, any specific with to run any specific independent variable, it's just that obtain overall error square, its average, divide divide this u hat square by the average, and run regress it on all independent variables. So if this particular average, sorry, this u hat square divided by average, if this is significantly related with the independent variables, then it means there is a heteroscedasticity, otherwise there is no heteroscedasticity. And what are the drawbacks now? If look upon if these methods, there are drawbacks with this method as well. I think it's given in Gujarati or somewhere else. Yeah, is it that only independent variable are linear in form? Means it's not always the case, right? It might be that x square is related with the u hat square, not simple x. So that's one of the limitation of this method. If it will be given, okay, it's not, yeah, it's given. With respect to that supposedly caused which is sensitive to normally assumption, general test of, yeah, one of the assumption in these tests is that these x variables are normally distributed, but that's not the assumption. If that will be the case, that will take in the next test, but means x variable that supposedly caused heteroscedasticity or the Bush-Pagan test, which is sensitive to a normality assumption, and that might be problematic in many situations. But more than that, is it that only the x simple that linear form of the x is related to u hat square or residual squares, but it might be that under root or any other form. So what we have to do about that? So in that case, is it that we can take any other form of the x variable or it's not applicable? So that might be one limitation of this method. So the next test try to overlook upon these assumptions, and that this next test, White's general heteroscedasticity test. It is that you can run this regression not on a simple linear form of x, but any of the form of x or any of the situation like x2 multiplied by x3, x square, x cube, means any of the form you think is might be a probable cause for this interrelation between u hat square and independent variable, that you can run. So that's the beauty of this next test. And again, the same null hypothesis that it is they are related to this or not. If all they are, this null is proof that they are all insignificant. All these relations are insignificant. There is no heteroscedasticity. Otherwise, there is a heteroscedasticity. So here, just running this regression, we have to see this multiply this r square with the n and that follow chi-square distribution. Then just see the level of significance. Sorry, p-value. So for this particular test, this is a very simple test. First, just run simple regression, obtain u hat, you generate a new variable u hat square, and run it on all the possible forms of x that what you might think is the probable cause. So that test is, the command for this test is estat im test comma white. So it will give you this heteroscedasticity chi-square. This is actually this particular value is n into r square for this particular model. The model is that we are trying to look upon the relation of u hat square with any of the form of x. So this value which follow a chi-square distribution. Now, if its p-value is less than level of significance, then we have to reject this null hypothesis. The null is homoscedasticity, which means all these coefficients are not statistically significant, equal to 0, that is a homostaticity. And if it's not, means if they are significant, then there is a case of heterostaticity, that is alternate hypothesis. And here it's proved that there is a heterostaticity. So this is the one of the another method of testing a heterostaticity. So I think it's enough for today. Tomorrow I'll just try to give you a glimpse of two more tests. This Conquer-Bassett test, and then I think Park test, Goldflag test. First, I'll try to do these two or three more methods which are given in these textbooks to identify the heterostaticity problem, and then try to look upon the solution for this problem. That okay, this is causing a change in the standard error because of heterostaticity. This standard error is going to change. That might change all the results based upon hypothesis testing. So what are the solutions for this particular problem? So after doing these two, three other methods which are generally we use to test heterostaticity, we will do this possible solutions for this particular problem. Any doubts so far? Anyone have any doubt?